In 1865, the French author Jules Verne published a novel detailing a plan to launch 3 men to the moon. The fictional journey began on the Florida Peninsula, with exactly 3 astronauts strapped inside the capsule. Verne calculated the rest of the mission parameters with mechanical precision. The craft would be constructed of hollow aluminum, and it would return to Earth by splashing down in the Pacific Ocean to be recovered by the United States Navy. 104 years later, NASA executed the Apollo 11 mission using those exact same parameters. The Apollo 11 command module was named Columbia. Verne's fictional cannon was named the Columbiad. These overlapping details are too specific to wave away as a lucky guess or a literary metaphor. The question is how a novelist working with pen and paper in Paris managed to accurately calculate the engineering of a space program that wouldn't exist for another century. Verne was not writing a fairy tale. Sitting in his 3rd-floor apartment, he worked through the actual physics required to reach escape velocity. Breaking Earth's gravity requires massive energy, but a rocket launched near the equator gets a significant speed boost from Earth's rotation. Working within U.S. borders, Verne calculated the Florida Peninsula offered the optimal latitude to capture this free energy. In the 1960s, NASA engineers looking for a place to launch the Saturn V program arrived at the exact same geographic conclusion. Geography is a fixed constraint. The physics of Earth's rotation forced both the novelist and the space agency to converge on a single strip of coastline to solve their thrust-to-weight ratios. Once the launch site was established, the next problem was mass. Moving 3 men into the vacuum of space required material incredibly strong, yet exceptionally light. Verne specified an aluminum cylinder. In 1865, aluminum was a rare and difficult to refine element, but it satisfied his mathematical requirements perfectly. NASA faced identical mass-to-strength constraints and built the real Columbia command module out of aluminum alloy. Inside that aluminum shell were the human subjects of these calculations, a crew led by Armstrong. And then comes the moment of the launch itself, a sequence written out in a quiet Paris study and executed live on television. The Saturn V ignited on the Florida pad, displacing thousands of pounds of thrust through intense chemical fire to push the capsule into the sky. Verne imagined a gigantic cannon embedded in the Earth, rather than a multi-stage rocket, but the underlying structural math dictating the vessel's material and the energy needed to break free from Earth was identical. Re-entry brought both capsules safely back for the atmosphere to splash down in the Pacific Ocean. And in both cases, the crews were successfully recovered from the water by the United States Navy. What makes this strange is the sheer amount of time that separates the blueprint from the mission, a gap of 104 years. Humanity had to painstakingly catch up to the math. It took nearly 4 decades just to achieve the first powered flight at Kitty Hawk. That was followed by years of dangerous, incremental milestones, from liquid-fueled test flights to the wartime V-2 program, all needed to replace Verne's theoretical cannon with practical propulsion. For an entire human lifetime, the novel sat silently on library shelves, while the world slowly forged the steel and harnessed the fire required to execute its instructions. Jules Verne was not a psychic, but the universe only has one set of physical laws. If you calculate the physics equations correctly, they will always yield the same answer, whether you are solving them with ink in 1865 or engineering in 1969.